everyone. So this is a class on an introduction to statistics for the psychological sciences. My name's Rob, and this is the first part of the fourth lecture in the course. There's going to be two parts to this lecture. In this first part, we're going to go over the standard normal distribution and what standardization is and how to standardize raw values. And then in the second lecture, we're going to use this process of standardization to be able to compare a distribution of our raw data to a standard normal distribution. And that's going to allow us to determine certain things about our distribution of scores, about our sample data. So if you find this video helpful, don't forget to like and subscribe. As always, over here are the PowerPoint slides, and let's just get started. Okay. So let's start by talking about different types of distributions that we will commonly encounter. Right? So the standard normal distribution represents a distribution that is symmetrical, right? Meaning it can fold, it's equal from the midpoint on one side to the other side, right? You could fold it in half and it would line up. And it's bell-shaped. One property of the normal distribution is that if it's perfectly normal, the mean, the median, and the mode are all going to be identical. They'll be equal. In addition, the standard normal distribution, right, which is a normal distribution in units of standard scores, right? It has a population mean of 0. Remember, that's mu. And a population standard deviation of 1. So in addition, there is a property of the standard normal distribution called mesokurtosis, right? It's a mesokurtic distribution. And what kurtosis is it's kind of like how many cases or points of data end up in the tails. And in addition, the normal distribution is asymptotic. I bet you have not heard that word in quite a while. Asymptotic means that it gets infinitely close but never touches. And what it's referring to is the tails of the distribution. The tails of the distribution fan out to infinity, right? But they never touch the axis. It never ends. And the normal distribution, the fact that it is asymptotic means that it's always capable of handling some kind of very extreme score out to infinity, either in the negative or the positive direction. So let's look at this picture of the normal distribution, or the standard normal distribution. So there's interesting properties. If we have a standardized, perfectly normal distribution where mu is 0 and the standard deviation is 1, there are interesting aspects. We can compute specific areas under the curve. So as you can see in this picture here, the proportion of cases that fall between -1 standard deviation and the population mean is 34.1%. And remember, it's symmetrical, so it's the same from -1 to 0 as it is from 0 to +1. And in addition, you know, the proportion between 1 and 2 standard deviations is 13.6. The proportion between 2 standard deviations and 3 standard deviations is 2.1. And only 0.1 percent of cases fall 3 standard deviations above or below the mean of a standard normal distribution. So these properties are interesting, and if we could somehow make our raw data in these units, we could leverage this property of the standard normal distribution and kind of infer how many people lie within certain standard deviation ranges above or below the mean. Now, oftentimes our data is not a perfectly normal distribution. So one type of deviation from normality involves deviations of symmetry. Typically, we refer to this as skewness, right? And there's 2 types. There's a positively skewed distribution and a negatively skewed distribution. So a positively skewed distribution is the tendency for scores to cluster, or for there to be a higher frequency of scores below the mean than above the mean. And so you can see here that a positive skew goes you can think of it as if the direction of the stretched out tail, the direction that tail is pointing, is the direction of the skew. So a positively skewed distribution has a stretched out tail pointing in the positive direction, while most cases fall below the mean, right? And as we talked about in a prior lecture, we referred to, like, if we were looking at the salary of Tesla employees and Elon Musk was in the room, he would stretch the mean out. And you can see this here in this skewed distribution. That would be an example of a positive skew, where the mean is being highly influenced by some outlier, and it pulls the mean away from the median and the mode. Right? Remember, if it was perfectly normal, the mean, median, and mode would all line up. So that is a positive skew. Negative skew is essentially just the opposite, right? So it's the tendency for scores to cluster above the mean and for the tail to be pulled in the negative direction. Now, in a standard normal distribution, the population mean will always be 0. So when we say standard, we're talking about a standardized unit, right? And any value below the mean is negative, and any value above the mean is positive. So another thing, you can kind of think about the normal distribution, or any distribution, whether it's symmetrical or not, it's kind of like being an infinite histogram, right? So it's almost like there's a bar graph underneath the curved line, but it's so fine, right? It's infinite. So if that's helpful to think of it in that way, go for it. So other deviations from normality don't involve messing with the symmetry of the distribution, but involve having too many or too few cases or observations in the tails. And so when a distribution is perfectly normal, we call it mesokurtic. But whenever it has a positive kurtosis, meaning that there are more people in the tails than would be expected with a normal distribution, we call that leptokurtic. And usually what this indicates is that we may have some extreme outliers in our distribution. So one way you can think about this, just to remember, leptokurtic means that the distribution is kind of peaky. It peaks up, and there's just and then it kind of fans out in the tails. So leptokurtic is like leaping, like the distribution is leaping. Now the opposite of a leptokurtic distribution is a platykurtic distribution. And this one kind of looks like a plateau almost, right? But what it is it's the tendency for less scores to be in the tails. So the data are clustered more near the center, towards the mean. And there's not the level of observations that you would expect in the tails of the distribution. So these are, skewness is one deviation from a normal distribution, and kurtosis is another possible deviation that a distribution can take that makes it not normal. Okay, so we've talked about this standard normal distribution. Well, what's this all about? Well, we have to first talk about what standardization is in general. And it's kind of like standardization is an attempt to resolve the issue of comparing apples to oranges, right? So you may have, the normal distribution is in units, the standard normal distribution is in units of standard deviation. But you may have collected data from a sample of people on their depression score, right? We're getting a lot of mileage out of depression examples in this class. But say you have people's depression scores. Well, how do you compare a depression score to the units of standard deviation in the standard normal distribution? We want to do that. We want to be able to compare or use the functions, the benefits of the standard normal distribution to be able to infer from our data. But how do you do it? How do you compare feet to standard deviation? Well, you have to convert it, right? We have to put our data in units of standard deviation. Now, standardization doesn't have to be standard deviation, right? It has to be, you're putting them in a common unit that is kind of agreed upon, that can be compared against. So one, I think, real world example of this is like the difference between back when we used to barter and using money. Money is essentially a standard unit. It's an arbitrary but accepted standard unit of value in the United States, at least, right? And most of the world. But, in the United States, we all agree we're going to use this standard unit of value. And, whenever we were bartering, it's like, I'm sure people had a heck of a time trying to figure out how many chickens a cow was worth, or, how many hours do I have to help you work in order to get a meal, or, things like that are simplified because you don't have this complexity of trying to estimate and guess how similar or different two different units of measurement are. If we standardize them and put them in units of dollars, right, it makes it easy. I can buy a hamburger and it's in the same units of dollars as if I buy a house. Same units of dollars. So standardization is the process of putting things in common units so that we can compare apples and oranges. Now, one common way that people standardize data, you may have heard, someone saying, "Oh, well, my child is in the 95th percentile in school," right? Well, so percentile is a type of standardization, right? So basically, a percentile rank is where you take the percentage of scores in a distribution that fall at or below a particular value. So like the example I just said, 95 percentile rank or 95 percentile means that, my child scored higher than 95% of the rest of the population. Now, there's some issues with percentile rank. So it describes the position of a score in a distribution in relation to the other scores in the distribution. And it's in a way kind of like the median, right? You line them up in order, figure out what position your score is at, and figure out what percentage is below that. And when you do that, you're putting it in the common unit of percent. But we have no clue, so we don't know how spread out the values are in that distribution. In other words, person 3 could have scored 4 points, higher than person 4, and person 4 could have scored 8 points higher than person 5. And so there's not an equal, you can't assume that there's an equal distance between the units, right? As a consequence, percentile rank is an ordinal measurement. It is an ordinal measure of relative standing. So that's kind of a weakness, because percentile rank does not take into account the position, or it doesn't take into account like the underlying distribution of data. It only shows the position of a score in relation to other scores, but it is lacking in terms of its ability to describe an underlying distribution. Okay, so what's an alternative to percentile rank? Well, the standard normal distribution is in units of standard deviation. And standard scores simply take raw scores that you collect, the apples, right? You collect scores in whatever units, depression, severity, feet traveled, whatever it is, and you convert those raw units into standard scores, which basically, let's just look at this formula, right? So we call a standard score a ZScore. And what it does is you basically are finding the difference of a particular raw score from the population mean and then putting it in units of standard deviation. Right? Essentially, when we're dividing something, we're putting it in units of that. So in essence, all we're doing is converting the unit of measurement. And we're also changing, in the numerator, we're converting a raw score into its deviation from the mean. So we're taking deviation from the mean and putting it in units of standard deviation. And that is what a Z-score represents. Okay. So we already went over this. So essentially, a z-score, what it does is it gives a particular raw score's distance or above or below the mean of that distribution in units of standard deviation. Positive scores, a positive z-score, once you convert your data into units of z, right, into a z-score, positive z-scores are always above the mean. Negative z-scores are always below the mean. Right? So remember, in the standard normal distribution, the mu is 0. Right? And the unit of standard deviation is 1. And so essentially what we're able to do is find where our data lie in units of standard deviation. And this makes it so that we're able to compare, to leverage these properties of the standard normal distribution to learn things about our distribution, our data. So basically, what we're doing here is just transforming, doing like a linear transformation. We can do it and then undo it, right? We can convert it into units of z and then unconvert it back into raw scores. But when we convert it into z, we can leverage the standard normal distribution and use the properties of the standard normal distribution to our advantage. So it's important to understand that this standardization process, it doesn't change the shape of our distribution of data. All it does is it makes it so that the mean is transformed into a value of 0 and the standard deviation is transformed to a value of 1. So this is going to wrap it up for this lecture. I hope this was clear. What we're going to do next, this was the logic behind why we standardize. In the next portion of this lecture, we're going to roll up our sleeves and actually do some problems that demonstrate how we can leverage the properties of the standard normal distribution to learn about things like what proportion of people scored above or below a certain value, right? What proportion of people are likely to have a depression score between, 6 and 7. And so we can look up proportions. We can also ask, what raw score would you have to be in the 95th percentile, for example? So we will dive into that next portion of this lecture, and I hope this was helpful. Have a good night.